Okay, how does a computer think? Because computers are actually pretty stupid, and it's really the engineering and the human work that goes into a computer that makes it appear smart. But computers by themselves can only do pretty much two things. Everything to a computer is either on or off. It's either yes or no. It's either true or false. They have two ways of thinking. So in your computer is full of many, many billions of bytes. And a byte is made up of 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. So your computer is full of these bytes. So we say byte with a capital B is 8 bits put together. All that these bits can do is determine if there's current, if there's electricity passing through it or not. And that way the computer knows if this bit is on or if it is off. So if the circuit lets current flow through this bit, the computer knows, okay, this bit is on. And maybe this bit's off, maybe this bit's off, maybe this bit's on, off, on, maybe that one's on. And believe it or not, just through having millions of yes and no's, your computer can actually do a lot of stuff. As we all know, computers are pretty impressive. But literally, behind the scenes, all that's going on for your computer is on and offs, true and falses, yes and no's. That's all that's really going on beyond the scenes. So let's take a step back here. Let's go back to kindergarten. So in kindergarten, we started learning about numbers. So give me a number. Well, I guess you can't. You're not talking right now. 653. Maybe in grade 1, maybe in grade 2, maybe in kindergarten if you were really smart. You would have learned, oh, okay, this is the ones place right there. You would have learned, oh, this is the tens place. And you would have learned, oh, this is the hundreds place. We live in a day-to-day world, in our science world, we live in a base 10 world. That means that our number system has 10 numbers that we work with. And those 10 oops, we don't need 10. And these 10 numbers, we can make any number in our world. That's math, we work with base 10, science, we work with base 10. Just our living world, we live in a base 10 world. A computer cannot make 10 decisions. This is too much information for a computer to have 10 options. A computer only knows on or off. That's all a computer knows. So we're left with 2 options. We're left with 1 and 2, option 0 and option 1. Option off, option on. False, true. So how do we do all of the beautiful things that a computer does with just 2 options? Well, you can spend years on this of studying and learning, and maybe some of you will once you go into your computer science, or if you do choose the computer science route. Let's just talk about numbers for now, because that's a pretty simple one to muster up. So you'll notice I said that this was the ones place. I said this was the tens place, and I said that is the hundreds place. I could have also wrote those places like this. This is the ones place, and is 1 not just 10 to the 0? Who's taking grade 9 math? I'm not too sure. 10 to the 0 is just 1. This is the tens place. 10 to the 1 is 10. This is the 100s place. Is that not just 10 to the power of 2? So notice this base 10 world that we live in, it's called base 10 because each of these number places can be represented as bases of 10. 10 to the 0, 10 to the 1, 10 to the 2. 1, 10, 100. All right, let's live in our binary world now. I've only got 2 options here. two options. That must mean I live in a base 2 world as far as computers go. So now I don't have a ones place and a tens place and a hundreds place. I have a 2 to the 0, I have a 2 to the 1, and I have a 2 to the 2. I've got a 2 to the 3, 2 to the 4, 2 to the 5, and so on. What's 2 to the 0? Well, anything to the 0 is just 1. So I'm running out of room. Sure, I'll just write equals. So this is the ones place. 2 to the 1 is 2, so that's the 2's place. 2 to the 2 is 4, so that's the 4's place. So I've got a 1's place, I've got a 2's place, I've got a 4's place, and if you keep going on, you've got an 8th place and a 16th place and a 32's place. Quite different than what we're used to working with, right? Normally this would be 1s, 10s, 100s, 1000s, 10,000s, 100,000s. In binary, we can't go that quickly. We got to go 1, 2, 4, 8, 16th place, 32th place. So, my paper's all mucked up. For example, so remember, we said this was the 2 to the 0, so this is the 1's place. This is the 2 to the 1, that's the 2's place. This is the 2 to the 2. So this is a 0, this is a 1. Oh, sorry, this is a 2, and this is a 4. So for example, how could I in binary, actually, I'm gonna add one more. This is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So this is my 1's place, my 2's place, my 4's place, and my 8's place. So how could I create the number 6 in binary? Because I can't just use 6. The computer doesn't know what 6 means. Well, how do I make 6 in binary? Well, hopefully you would have told me, these are the numbers I can work with. And how do I make 6 out of these numbers? Well, I can make it out of, you can only make it one way. And hopefully you would have seen, okay, I need a 4 and I need a 2, because 4 plus 2 is equal to 6. So in this half byte that we have of 4 bits, in your computer, the actual physical CPU part of your computer, you would shine light through the 2's place and the 4's place. So you would go like this. 1 means on, 0 means off. This is how your computer knows what 6 is. And this is what we call binary. It's how your computer deciphers base 10 numbers into binary. Bi means 2, something that your computer can actually muster up and make sense of. So light would be shining through these 2 bits, and there would be no light or no electricity shining through these ones. And your computer would know that you are talking about the number 6 based strictly on light shining through or electricity passing through certain bits of your byte. Hang on. Still not convinced? This is not 1s, 10s, 100s, 1000s. This is the 1's place, the 2's place, the 4's place, the 8's place. How do you make the number 7? Well, pretend this is half a bit. How do you make 7 out of these 4 numbers? Well, I clearly don't need 8, and I clearly need to add 4 plus 2 plus 1. Bum, 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 gives me 7. So light needs to shine through this bit, this bit, this bit, and no light needs to shine there. So 7 in binary is 1, 1, 1, because I've got electricity on. You could put a 0 in front of there if you wanted. It's not really necessary. Let's do one more. how do I make the number, let's do a big one. Let's do 13. How do I make 13 in binary? Well, I can go 8 plus 4 is 12, and I need one more for 13. So I need electricity to pass through this bit, and this bit. And this bit can stay off. So in my computer, I got power, I've got these bits turned on, and this bit turned off. So 13 in binary is 1101. Makes sense? It's kind of complicated, but very important concept to know.